In this video, we're going to go ahead and take a look at our other trends that we're able to find on the periodic table. The first trend that we're going to take a look at is going to be our ionization energy. This is going to be the energy needed to remove an electron from an atom. So whenever we add or need to remove something from an atom, it is going to take energy in order to do that. So our ionization energy is going to be the energy needed to remove an electron from that atom. Now, why this trend happens is because, first, our shielding effect. So as the more inner electrons are added, the more shielding the valence, allowing them to be removed more easily. So whenever we have more electrons, they are easy to take from them because we just have so many electrons that we're able to take from. Now, nuclear charge is that as the nucleus gains more positive charges, that force of attraction on the valence electrons is going to increase, causing more energy needed to remove an electron. So as more electrons are added, the easier it is to remove them. But as we add more protons to the atom, the harder it will be for us to take an electron from that atom because of that force needed. If we take a look at the trend on the periodic table, it is going to increase upward and increase to the right. So this means that it's going to require quite a bit of energy in order to remove an electron from helium. But if we take a look at francium, it's going to require a very small amount of energy to remove an electron from francium. Let's go ahead and take a look at some practice with this. All right, so first thing, let's go ahead and draw our trend of increasing up and increasing to the right. If we take a look at nitrogen and oxygen, we should notice that oxygen is going to follow that trend of being the highest ionization energy required. So our oxygen will be what is going to be the answer. If we take a look at our next one, so we have our neon, we have fluorine, and we have chlorine. Following this trend, so we're going to increase up and increase to the right. So if we follow that trend, we should notice that neon is going to be the highest ionization energy. So that will be our Ne. Taking a look at our next one, we have our nitrogen, we have arsenic, and we have our fluorine. Same kind of idea as number 2. Our trend is increasing up and to the right, which means that fluorine will have the highest ionization energy out of these different elements. Now, if we go ahead and take a look at electronegativity. So this is going to be the force of attraction an atom has on electrons. Now, the electronegativity indicates the relative ability of its atoms to attract electrons in a chemical bond. So most of the time, whenever we are talking about electronegativity, it is going to be those electrons in a chemical bond. So why this trend happens, first being our shielding effect. As more inner electrons are added, the more shielding the valence electrons have, causing the nucleus to essentially lose control over them. So the more electrons we have, the more chaotic it is, the more likely those electrons are to be removed or to form a bond with another atom. Now, then we have our nuclear charge, is that as the nucleus gains more positive charges, the force of attraction on those valence electrons is going to increase, causing more control over those electrons. So as we gain more positive charges, essentially the tighter the nucleus has on the electrons on the outside. Now, with our electronegativity, because most of the time we are talking about it in terms of a chemical bond, our noble gases do not have electronegativity because they already have the maximum number of valence electrons. And so, because they have the maximum number of valence electrons, they do not like to form bonds with other atoms. And so, just because they don't like to form bonds with other atoms, they tend not to have an electronegativity to them. So if we take a look at the trend for electronegativity, this is going to increase up and increase to the right. Now you'll also notice that the noble gases are blacked out. So noble gases, their electronegativity will be essentially zero. So your noble gases will always have an electronegativity of zero as far as we are concerned. So this means that the highest electronegative element on the periodic table is going to be the fluorine. Let's go ahead and take a look at these three example problems. So we're going to arrange the following elements by increasing electronegativity. So we need to remember our trend is up and to the right, excluding the noble gases. So taking a look, we have our boron, we have our sodium, we have our fluorine, oxygen, and neon. So increasing electronegativity. So whenever we're increasing electronegativity, we're going to go from the smallest to the largest. So if we follow this trend, we should notice that sodium is going to have the smallest electronegativity. But we have to remember the noble gases. So the noble gases for us are going to have an electronegativity of zero. So in this case, our neon is going to have the smallest electronegativity. Once we have neon, then we're able to take a look at our normal trend. So it'll be our neon, then we'll have our sodium. Looking next, we'll have our boron, oxygen, and then our fluorine will be the highest. Let's take a look at example number 2. We have our sulfur, we have our sodium, we have our magnesium, we have our chlorine, we have our argon. Right, so we should pretty much almost immediately recognize that argon is a noble gas and its electronegativity will be zero. So this will be our AR. Once we have the noble gas as the smallest, we're able to continue as normal. So we'll have our sodium next. Then we're going to have the magnesium, then our sulfur, and then chlorine being the largest in this group. Taking a look at our third one. So we are going to have the nitrogen. We're going to have our phosphorus. We're going to have our antimony. We're going to have our bismuth, and we're going to have our arsenic. If we take a look, we don't have any type of noble gases for us to be concerned with, so we're able to follow the trend as normal. So we're going to increase from the bottom to the top. So that means that our bismuth will have the smallest electronegativity. After that, it will be our SB, and then our AS, then our P, and finally our N for our nitrogen. So that will be increasing our electronegativity for that third set of elements. The last trend we're going to take a look at is going to be our reactivity, which is going to be the ability for electrons to form bonds. And the big thing about forming bonds is that it is all about the valence electrons. So atoms want to have a full outer shell, which is going to be that octet rule. So they all want to get to 8. So our atoms will gain or lose electrons in order to achieve that. Now, why this trend will typically happen is going to be based mainly off of our shielding effect and our valence electrons. So our shielding effect, as the more inner electrons are added, the more shielding the valence electrons have, allowing them to react more easily. So again, the more electrons we have, the more chaotic it is, the more likely that electron is going to form a bond with another atom. All right, so we have our reactivity. One of the big things that we will notice with this is going to be the noble gases. The noble gases do not have reactivity to them because they have a full outer shell. They have that full octet to them. Now, the reactivity trend is kind of confusing because we do split it up into the metals versus the non-metals. So remember that the metals are on the left side of the periodic table, the non-metals are on the right side. So for the metals, they are going to increase in reactivity going to the left and going down. Now for the non-metals, they're going to increase in reactivity going to the right and increasing upward. So this means that francium is going to be the most reactive metal that we have. And then we have fluorine, which is the most reactive non-metal that we have. Now, just everything to make sure, remember that our split between metals and nonmetals is going to be this black line, which will be right here. So this will be our split between metals and nonmetals. So anything to the left of that is going to be a metal. Anything to the right will be a nonmetal. Taking a look at these three practice examples, let's go ahead and compare these. So we have our fluorine versus our beryllium. So we have our beryllium and we have our fluorine. Now, one thing that we do have to pay attention to is going to be our valence electrons as well. So remember that in group one, these have one valence electron. These have two valence electrons. We have our three valence electrons, four valence electrons, five valence electrons, six valence electrons, seven valence electrons, and eight valence electrons. Now, based off of the number of valence electrons, these are either going to gain or lose electrons in order to achieve that octet that we have. So, everything in group one is going to want to lose that one valence electron, and so these will typically have a negative one charge. In group two, two valence electrons, it's easy to lose those two valence electrons, so everything in group two will typically lose those two valence electrons total. Now, whenever we lose electrons, remember that the charge will become positive because what we're doing is that we're losing negativity. So whenever we lose negativity, the atom will become positive. Right? Now looking at group 13, they have three valence electrons. So they are going to want to lose those three electrons. Whenever we lose that negativity, though, we become more positive. That will be our plus three charge. Now, looking at group 14 or group 4, these and everything are able to do either. So they can either gain or lose electrons. So these will typically have a plus or minus 4 charge to them. Our 5 valence electrons, they are going to want to gain electrons. So they will typically gain 3 electrons. So this will be our negative 3 charge, negative 2 charge, negative 1 charge, and then the noble gases do not have a charge at all. So taking a look between our fluorine and our beryllium now that we have all of our information. So our beryllium, it will want to lose 2 valence electrons in order to become stable. Our fluorine will want to gain one valence electron in order to become stable. So the question to really ask yourself is, what is more likely to happen? Is it more likely that the beryllium will lose two valence electrons, or is it more likely that the fluorine will gain one valence electron? And so the best way to think about this is which one is going to be easier to achieve. And doing the least amount of work is going to be the easiest thing to achieve. So the fluorine gaining one valence electron is going to be really easy. And so that means that it is going to be highly reactive because it is easy for that fluorine to gain one valence electron in order to become stable. So this means that our fluorine will be our most reactive element out of these two. Taking a look at our next set, we have our AS and we have our GE. All right, so we have to take a look at our valence electrons. Now, our GE, it can either gain four or lose four. Our AS, it will need to gain three electrons. So, asking yourself which one is going to be easier to achieve, we should come to the conclusion that our arsenic gaining three electrons is going to be easier than the germanium having to gain or lose four valence electrons. So our arsenic will be able to quickly gain three more valence electrons in order to become stable, making the arsenic the more reactive element. And taking a look at our oxygen versus our sulfur. All right, so we should notice that the oxygen and sulfur are both in the same column, which means that they both need to gain two electrons in order to become stable. So we're not able to go off of our valence electrons in this case. So what we need to go back to is going to be our reactivity trend. And because this is on the non-metal side, we should remember that it is going to increase to the right and it increases upwards. So increasing upwards should mean that oxygen is going to be the more reactive element because it is closer to fluorine, which is our highly, highly reactive halogen. So oxygen is going to be the most reactive element out of these two. And that is going to be how we take a look at reactivity.